Hello everyone. Today we're going to show you how you can do A-Causal modeling and create components in Dyad. In this tutorial, we'll show you how you can build a simple RLC circuit from scratch without the aid of any external libraries, and then we will simulate and analyze that model. If this is your first time using Dyad, please make sure to go to the installation and getting started pages in order to set up your environment and to get familiarized with Dyad. That being said, let's move ahead with today's lesson. Here inside of VS Code, with my Dyad Studio extension installed, the first thing I'll do is create a component library. To do so, I'll bring up the command palette, type out Dyad, and select Create Component Library. When prompted, I'll give my component library the name RLC Components, and then I'll hit enter. And I will save my component library inside of this folder on my desktop. Here I see an instance of VS Code with my component library folder structure exposed on the left side. So what I'll do is I'm going to start up the Julia REPL by opening up the command palette and typing out Julia, and I'll select Start REPL. In the REPL down below, I'm going to enter the package manager by hitting the close bracket key. And I'll go ahead and instantiate my environment. Once my environment is instantiated, I'll type out the command test to confirm that everything is working properly. Once you see something like this down below, it means your environment is set up properly and everything is working. Okay, so now I will exit the package manager by hitting the backspace key to return to my Julia REPL. Okay, so now let's move forward with creating our Dyad components. So remember that any models that we have saved inside of our Dyad folder, the Dyad compiler will look at that and generate corresponding Julia files for us to use. But we just need to concern ourselves with the code we place inside of this folder right here. So what I'm going to do is right click on this folder and create a new file. And I'm going to name this file rlc_parts.dyad. Let's start with creating a connector. So when we model physical systems, we always start by defining connectors. And connectors are used to represent the information exchange by components that interact with one another. So here, we're going to define a pin. This is a connector for an electrical system. You can see here that this pin has a potential variable V for voltage, as well as a flow variable I for current. And once I hit save, I can see that a corresponding pin Julia file is created in my generated folder. The next thing we're going to do is we're going to define a resistor component. Remember, our ultimate goal here is to build up an RLC circuit, right? A circuit with a resistor, inductor, and a capacitor. So let's define a resistor component right here. And inside of this resistor component, we can see that we have a positive pin as well as a negative pin. Our resistor has two variables, one for voltage, one for current, as well as a parameter R, indicating the resistance of our resistor. In the relation section, in other words, the physical equations that enforce the behavior of this resistor, we have our resistor component. Our resistor has a positive and a negative pin. It has two variables, one for the voltage across the resistor and one for the current through the resistor. And then finally, we have a parameter R indicating the resistance for the resistor. In the relation section, we have a few equations which dictate the behavior of our resistor. We have the voltage across the resistor is equal to the voltage difference between the positive and negative pins. The current through the resistor is equivalent to the current through the positive pin. The sum of the current through the positive and negative pins must be 0, as well as this equation for Ohm's law. Okay, so that's our resistor component. So next, let's define a capacitor component. So here we have a capacitor component. Our capacitor consists of a positive and a negative pin. It has two variables, one for voltage, one for current, a parameter C for the capacitance, and then these relations down below. We have an equation for voltage across the capacitor, current through the capacitor, this equation relating the current through the positive and negative pins, and finally, this equation down below, which relates the current derivative of voltage and capacitance. So looking at these resistors, our resistor and capacitor component, you might notice some similarities. Both our resistor and our component, both our resistor and our capacitor have a negative pin and a positive pin, and they also both have a voltage variable as well as a current variable. In addition to that, you can see that in our relations for each of our components, both the resistor and the capacitor share the first three equations. Let's say we want to avoid writing redundant code like this. Okay, how can we avoid repeating ourselves and to take advantage of the structural similarity between these two components? So what we're going to do is we can define a partial component inside of Dyad. A partial component is one that is not complete on its own, but it can be used to build up a complete component. Let's demonstrate that right now. So let's rebuild this capacitor and resistor. So what I'm going to do is I'm going to delete our definitions for it. And what we're going to define is a partial component called one port. Our one port has a positive and negative pin. It has the variable I for current, variable V for voltage, as well as these three relations, right? So these are the similar variables, components, and relations that the resistor had, as well as the capacitor. So with this as our partial component, one port, we can now define our resistor. So here we can see that our resistor component inherits or extends from one port, meaning it inherits all the variables, components, and relations that one port has. In addition to that, our resistor adds some of its own elements. Our resistor also has a parameter R for resistance, as well as Ohm's law right here. So how do we define our capacitor? Very similarly, our capacitor also extends from one port, meaning it also inherits everything you see right here. In addition to that, our capacitor also has a parameter for capacitance, as well as this relationship you see right here. So that is how we can take advantage of similarities between two components by building one partial component and allowing other components to inherit or to extend from that partial component. So next, let's go ahead and define our inductor in a very similar manner. Our inductor will also extend from one port. It has its own parameter L for inductance, as well as this relation down here relating the inductance, current, and voltage together. We'll also define another component called step voltage. This step voltage component extends from one port. It has a parameter for voltage as well as step time. Here, we can define a step voltage component, which also extends from one port. Our step voltage component will have a parameter VF 32, as well as a parameter step time of 5. And under the relations, we can see that the voltage for our component will be 0 if the simulation time is less than the step time of 5. Otherwise, if the simulation time is greater than the step time of 5, then the voltage across this component will be VF, in other words, 32. And then finally, what we'll do is we'll define a ground component, which consists of a single pin and the voltage across that pin is 0. So we've just built or created all the components we need to build up our RLC circuit. So make sure you have saved this file and that you can see the corresponding generated files in the generated folder. So the next thing I'll do is I'm going to create a new file inside of my Dyad folder, and I'm going to name this file rlc.dyad. You're able to put as many components as you like in a single file. I just kind of like to organize my components a little bit by putting them in separate files. But this is up to a matter of taste, and you can do it how you'd like. On the left side, or pardon me, on the right side, we have our RLC parts.dyad file with all the components we created, our pin, our one port resistor, and so on. And on the left side right here, we have our file in which we'll define the RLC component. So here is our definition for our RLC component. We have a resistor, a capacitor, an inductor, a source, and a ground component. And of course, all 5 of these components of our RLC circuit are instances of the components that we created earlier inside of our RLC_parts. So we're using the components that we just created. In the relations, we have initial conditions for the current through our inductor, as well as the voltage across our capacitor. And here we use these connect statements to connect our components together, thereby enforcing the physical relationships in between each of those components. So now that we have our RLC circuit, we can go ahead and define our analysis. So here we have an analysis called sim RLC. This analysis inherits from or extends the transient analysis type. And the model that we're gonna use inside of this analysis is an instance of the RLC model. Of course, this RLC model is what we defined right here. Once I have that saved and the corresponding files in the generated folder are generated, I can go ahead and simulate this model. So down here in the Julia REPL, I'm gonna bring my library into scope by calling the command using RLC components. Once our library has been precompiled, we'll bring in the plots package to help us plot our results. I'm gonna carry out this simulation and store the result inside of my result variable. So define a variable called result, and I'll set that equal to the return value of our analysis. Once the simulation is done, we can plot our result using the following command. And here we have it. In this plot, we can see the value of the voltage across the capacitor and the current through the inductor for our 10-second simulation. And this makes sense because our sim RLC analysis extended from the transient analysis and it used a stop time of 10. So that's what you see right here. In summary, what we did here today was we defined various components inside of our RLC parts.dyad file. We defined a pin, a partial component called one port, and resistors, capacitor, inductors, and step voltage, all of these extending or inheriting from one port, and also this ground component right here. We use those individual components that we created to build up our more complex RLC component, as you can see right here. Once the RLC component was created, we defined an analysis using the RLC model, and then we simulated and plotted our results. Now, you might be wondering, are there any included connectors or components or anything like that inside of the Dyad package? So it turns out the answer is yes. So over here, back inside of our Dyad documentation, here I am. Remember, this is where we started, Acausal modeling and creating components tutorial. On the left side, if I scroll down, I can see that we have areas for some component libraries down here. So let's see what's in the standard Dyad library. So what you get with Dyad out of the box. So here, this is the documentation for the Dyad library. And if I scroll all the way down, here's a definition for a pin. So this is what we created earlier, right there. This is the pin connector. So this already exists inside of Dyad. So you don't actually have to define it like we did. You can actually just use it out of the box right here. Similarly, if we go to the electrical components library on the left side over here, we also have a one port component, as well as a resistor, capacitor, and inductor. So all things we can take advantage of. So while what we did today inside of the tutorial is build an RLC circuit up from scratch without the use of any component libraries, in practice, you of course do probably want to take advantage of the standard components that come out of the standard libraries. So if you would like to see how you would create that same RLC circuit, but taking advantage of the standard libraries, the very last section of this getting started tutorial right here, at the very bottom, we actually walk you through how you can generate an RLC circuit using the standard libraries we provide for you, okay? So make sure you also take a look at this workflow so you understand how you can create a RLC circuit using standard library components. But of course, what we wanted to show you here today is how you can do everything from scratch to give you a fundamental understanding of this workflow. And that's it. That concludes today's tutorial. I encourage you to spend time on our documentation website. We have plenty of tutorials showing you how to do various things, playing with various features. And please reach out if you have any questions about Dyad or anything JuliaHub related. Thank you for your time.